In this video, I'll show you how to do hypothesis testing for the slope in simple linear regression. So we've fit the model now, and we've found r squared. And the next thing we're going to do is test the slope. So to do that, we're going to calculate S here. And S is often referred to as the standard error of the estimate, or sometimes the regression standard error. And it's calculated as the square root of the mean squared error. And the mean squared error is the sum of squared errors divided by the degrees of freedom for error. The degrees of freedom for error is 8. It's sample size minus 2 for simple linear regression. So if we take the square root of the mean squared error, we get 13.829, and so that's the standard error of the estimate. So the regression output is often summarized in a series of tables, and one of them has the parameters from the model, or the coefficients from the model. The intercept is B0 and the slope is B1. And we're going to focus on the slope. So the estimate, I've just written it here, I've copied it from up here, which is where we calculated it before. So the estimate is 5. And then the standard error has this formula. It's S divided by the square root of the sum of the x minus x bar squared. Okay, so this was something we calculated before. So we can take the square root of it and then calculate the standard error here for the slope estimate. And then the test statistic, it's a t statistic. It's simply the ratio of the estimate over the standard error. So that comes to 8.62. And then to assess the this using a hypothesis test, we're going to do a two-tail hypothesis test, where the null hypothesis is that the slope is 0 in the population versus an alternative hypothesis that the slope is not 0. So for a two-tail test, we'll use t.dist.2t to get the p-value, and the degrees of freedom is given by the same degrees of freedom we used over here when we calculated S. It's, for simple linear regression, sample size minus 2. Sample size is 10, 10 minus 2 is 8. So a t-distribution with 8 degrees of freedom has a two-tail p-value corresponding to 8.62, that is 0.00003, pretty small. And that's because this t-statistic is way out in the tail. So for a significance level of 0.05, for example, this p-value is a lot smaller than 0.05. So we would reject the null hypothesis that the population slope is 0 in favor of the alternative hypothesis that the population slope is not 0. In other words, we found a significant linear association between y and x. So that's what that tells us. We could also calculate a confidence interval for the slope. So as an illustration, here's a 99% confidence interval. So I'm using t.inv.2t with first argument 0.01 to find the critical value for the t-distribution with 8 degrees of freedom. And if I multiply that by the standard error here, and then do the estimate plus or minus that margin of error, I'll get 3.05 up to 6.95, so we're 99% confident that the slope, the population slope, is in our interval. So that's one type of hypothesis test we can do, a t-test. We can also do an f-test, and it turns out the f-test in simple linear regression it's equivalent to the t-test, and we'll see that because we get identical p-values. But let's just run through the details quickly. So down here, you might look at that table and go, that looks familiar. Well, it is. It's an analysis of variance table, just like we studied in the last lesson. And the table has a row for the regression, and a row for the error, and a row for the total. So these sums of squares, these were what we calculated earlier when we talked about R squared. So there's the sum of squares for regression, sum of squares for error, and total sum of squares. The degrees of freedom for each of those numbers, there's 1 degree of freedom for the regression. There's 8 degrees of freedom for error. We already talked about that. And then there's 9 degrees of freedom in total because the sample size is 10, and the total degrees of freedom is always given by sample size minus 1. And then the mean square, we can calculate a mean square for the regression by dividing 14,200 by 1. And we can calculate a mean square for error by dividing 1,530 by 8. And then the F statistic is the ratio of those two mean squares. And then the p-value comes from an F distribution with 1 numerator degree of freedom and 8 denominator degrees of freedom. And it's the tail area in the right tail, because an F distribution is always non-negative. And that tail area comes to 0.00003. It's the same as the p-value we got here, and that's no coincidence. For simple linear regression, these p-values will be identical. And that's because there's a relationship between the t statistic and the F statistic in simple linear regression. This F statistic is actually the square of this t statistic. So we get the same conclusion. With such a small p-value, we reject the null hypothesis and in favor of the alternative hypothesis, and conclude that there's a significant linear association between sales and population for this chain of pizza restaurants. Okay, so let's see where this output can be found when we run this regression in Excel stat. So we'll do linear regression. And then we'll OK this. And then we'll try and find where the parameter table is and the analysis of variance table. Okay, so let's scroll down. Okay, so there's the analysis of variance table right here. So all these numbers match the numbers that we calculated by hand. And then here's the parameters table here. And these numbers match the ones we got by hand as well. Excel stat, by default, it gives you a 95% confidence interval. So that's why these numbers differ from what we got, because we calculated a 99% confidence interval. It also gives you a p-value for testing the y-intercept, but we're not interested in that for this discussion. Okay, so that's how to do hypothesis testing for the slope in simple linear regression.